Get started. Check. Yeah. All right. Okay. So, just some reminders and announcements about stuff coming up. So I did finally post assignment 5. These things are taking me longer than I was expecting to set up. My plan is probably to go over that a little bit here first, see if anybody has any specific questions on that, since we can look at the actual content of it now. I still have kind of the due date as the end of this week. I can be flexible on that, so we only have half week next week. I think I've mentioned we're probably not going to be meeting next week. So of course Thursday is off, but I'm not planning on meeting on the Tuesday. But for this assignment, we've still got assignment 6. So, but yeah, no later than like Tuesday or Wednesday of next week, you should really try to get assignment 5 submitted. So I still have the deadline on Friday, but there's some flexibility. You can keep working on it this weekend, and the start of Thanksgiving week if you're still doing stuff by then. So
we can sign it for the next week, right?
Yeah, so it'll be okay if, say, Tuesday or so next week, if you submit it. And then beyond that, also we'll talk a little bit about dimensionality reduction and principal component analysis today. I hadn't realized, but I didn't have the notebooks in there for the Unit 13 and the Unit 14. That should say Lecture 13 there. But those are in the class repository now, so you might want to do a git pull if you want to see these notebooks I'm going to look on here. Again, I'm going to try and get the actual final assignment 6 here posted this week. We'll see if I can get it up or not. So, but that will have to be due that first week in December. And don't forget about the final project as well. So I hope everybody's working on that. So we can discuss that some more. But I haven't looked at that in a bit here. So I encourage you, if you're not making like regular commits, at least looking at it every week. At this point, you probably should be looking at it 2 or 3 times each week, making a little bit of progress, getting the commit pushed up there. So just to make certain that you don't do everything on the last at the last moment. Okay, so let me just kind of go over the assignment 5 a little bit. I won't spend too much time on this. See if anybody has any questions. Make sure everybody's kind of clear on what's to be done on this. So I did change my mind a little bit from what I was discussing. So we are using a data set. I'm asking you to use a data set from the Fetch OpenML, from the OpenML site. In fact, you can click on this link if you want to see the data set. So I probably should have put this on my list of stuff. There's lots of good data sets in here that would have been suitable for the final project as well. This is one of them. So that Fetch OpenML that you've seen before to load, like MNST, you might have used it for some other data sets. Any data set on here, you can use that to load. So I didn't give that to you, but you really just need the name and use the examples of fetching the MNST data set in order to get it. I don't know if you can see this, but I did give a little bit of an open-ended. I did ask you to, on this first task, show that there should be 10 features in this data set. If you load it correctly, they're all numeric. There shouldn't be any missing data, but you might want to confirm that. I asked you to confirm that yourself, so just check that it looks like all the numeric features have no NAs or NANs in there. I didn't ask you to do any scaling or anything. In fact, afterwards, I looked at it, the scales, the ranges of all the features. There is some differences on that, so there is a possibility that if we did some scaling, we might be able to improve the performance that you'll get, but you shouldn't do that. Just use the features as given. Don't apply any scaling or anything. A little hint for people watching this, or you guys are here, I do ask you to do one plot on that first part as well. So you will have to figure out the correlation between each of the 10 features and the target label that you're trying to predict. So this is a binary classification task in this case, and there's only 19,000 plus samples on this data set here. So 19,020 instances. So there's really only 10 features. I don't know why it's 12. I think there's like 11, but one of the columns in the data set that you load raw is the label. So that might be a mistake. I think that should have been 11 or 10 there. So. Okay, I started saying, so I did ask you to make one kind of plot here on this first task, but just kind of as a hint on that, remember that negative correlation is just as possibly useful as positive correlation. So it's really the magnitude of the correlation, not just the largest number. So I'm really looking for the most correlated features, where something that's highly negatively correlated is still highly correlated. So, and there is one other thing, is there's a little bit of data cleaning because when you load, if you load this correctly, you are required to use the fetch openML function from scikit-learn, so load it through that route. But when you load it, you will get strings or objects for the labels, so you will have to use an encoder. If you're not careful, you're going to end up encoding the wrong thing as the 1 and the 0. So you will have to do some things to explicitly ensure that the correct label is encoded as 1, the positive case, and the other one is 0. So for this data set, it's interesting. I think they've done competitions with it, although I think this is just a artificial data set that was created for a competition that looks kind of like the real data set they get from these telescopes. But in this one, it's binary classification. The signal, the positive case, is going to be labeled as G. So this is gamma or whatever. And then the negative case should be the H's. So if you have background or no signal, those are labeled as H's when you fetch this data here. So data's a little bit skewed, so there's more positive than negative cases there. So just if you always guessed 1, you should get about a 60% performance on this data set here. So you should be able to improve that if you do everything as is asked for in the assignment here. Let me know if there's questions on this. I'll only go over this once since we just got this week here to work on the assignment 5. Task 2 is kind of more of a utility function, kind of a warm-up, so some more practice on Python. But we've seen examples of using train test split. So I think I probably described this adequately, but I am requiring you to use the scikit-learn train test split. You just have to call it twice to make another function that can do a 3-way train validation test split. So the idea would be to call it once to split it into the train data and all the rest of the data. So we're going to be using the first 10. We're going to be using 10,000 samples to do our training. And then that leaves a bit over 9,000 samples, and we're going to split those evenly between the final validation and final test set. So you should end up with 4,500 and a little bit more in both the validation and the test set. And also, as I mentioned, if you read the description, I did want that function to work to set the random state so that we can call it, so we can use it to do some reproducible code so you get the same train test split. In order to do that correctly, you have to use the random seed parameter both times when you call train test split. So if you don't, it resets the seed to something random if you don't specify that on the train test split. So you should set the random state both times. And of course, you do have to use the scikit-learn train test split to be able to pass the test, to get the exact same split that we're expecting on the second function here. So, all right. So hopefully those first two will be warm-ups for most people. The third one is, I did make it a little bit more than the example that we saw, but it's pretty similar to the example. I am asking you to make 5 classifiers here and combine them into a voting ensemble. Okay. So hopefully this is clear. If you haven't read this yet, basically just just use the default. So don't specify any parameters for these except logistic regression, so you don't get convergence errors. Use a SAG solver and up the max iterations. So that should be the only. You should only change the parameters for logistic regression and only use those 2 parameters. And also, we're going to be using your voting ensemble both to try out hard and soft voting. You should know what that means now. But you should go ahead and just always create the support vector classifier that it supports the probability. So set the probability true. Right? So is that clear enough? So otherwise, besides logistic regression and support vector classifier, the other 3 should just use the default, so you shouldn't specify any parameters for that. And I discussed it a little bit. So an MLP classifier, we don't talk about that in this class. We don't talk about neural networks. It's a basic neural network is what a multi-level perceptron is. So. But it has the same interface that you should be familiar with. So you can create the instance and you can add it to the list of estimators for the voting ensemble, and it will fit it, and it supports making probabilistic predictions, so giving you a confidence for the 2 classes. So you can use it both for hard and soft voting. All right. So yeah, if you do that, I'm not doing a whole lot of testing on this. Just as a hint, if you're doing that right, you should get, if I can remember right, you should get like 80% or so usually on the hard voting with the voting ensemble, just using all the default parameters, which is better than just always guessing 1. So it is doing something, and I think that mostly, if you look at the test for this, I'm mostly checking that you do use the 5 estimators that I asked for, and for the first one that you're using hard voting, and that the final accuracy for each of the individual estimators is reasonable. It's like something above 0.75 or something above the baseline of just guessing always 1. Oh, and by the way, so I do ask you on the task 3 to actually, so this function returns back, the only thing it returns back is a voting ensemble, a voting classifier. All right. But we saw examples of this. You can access the individual estimators. So I ask you, after you create that function and get the test pass, to access the individual trained estimators in the voting classifier and show the accuracy on both the training and the validation data. All right. So be careful. This is kind of a warning for people. Be careful. Make certain, when you train the voting ensemble and the stacking ensemble later on, the base estimators need to be trained on the training data. Okay, so the thing that's returned from the task 3 function, your task 3 voting ensemble, should be trained on the training data. Yeah, we passed that in, so yeah, maybe it shouldn't. It should be hard if, as usual, you should not modify these cells, right? So you need to be using that data to train your estimators. But yeah, when you're accessing these, you can access both the original estimator untrained as well as the trained estimator. So make certain that you are accessing the estimator that got fit when you do this cell here, and reporting its performance for all 5 of them on the data it was trained with, as well as just the validation data. And then give also a report of the whole ensemble. You should find, so I picked this, the performance improvement isn't great, and in fact, you'll probably find maybe a percentage, maybe a 0.5% that the hard voting does over the best individual estimator. So it may or may not be significant, but it usually should do it the same, if not just a little bit better, that you'll find on your result for the hard voting ensemble here. Okay. And then you don't have to really do anything for the second one, so except you do have to. There is a third parameter for the task 3 function you have to write, so you have to be using that correctly. So if you're asked to create an ensemble that uses soft voting, make certain that you're doing that. That is part of the test here, so you won't pass these tests if you're not doing that. And again, all you have to do, the base estimators should all be the same, so you don't have to re-report the performance of all the base estimators. But again, here, I tried to pick this data because it does show you should get a bit of a better performance here. It'll be small, but it'll be 1.5%, 2% better than the best base estimator when you do soft voting here. So small, but probably significant performance boost. Okay, test 4 is a little bit more open-ended, but it should be relatively straightforward. I just asked you then to create a random forest or an extra tree. So create one of those bagging ensembles, so a bag of trees ensembles that we talked about. I do ask you to maybe explore the parameters on your own. So if you're really motivated, you could even do a grid search on some parameters and stuff and try and really optimize it. Probably not really necessary on this assignment. So if you try the basic, most important parameters, you should find that you can easily find bagging ensembles that do better than the soft voting classifier. So I can't remember, but you probably can get like 85%, 88% accuracy, somewhere around that on this one, right? You should get that, right? And as a reminder, I think I say it on here, but the most important parameter for a bag of trees is probably the number of estimators that you have it generate, right? So the default is like only 100, which may not give you real great performance improvement. So you definitely want to try and increase the number of estimators. All right. And then the last 2 tasks are about creating a stacking ensemble. So I tried to make this so that it will be more understandable than I have done in the past on this assignment. So in particular, the first task 5 is to write a utility function. This is really actually pretty simple. I don't want to give it away too much, but really there's one thing you can do from the NumPy library, basically, that is most of what this function is supposed to do. Well, that's not true. So you do have to basically, this function for the task 5, we pass in the voting, a voting classifier. So that's what's happening here. So what you're expected to do is access the individual estimators, like you had to do for the previous task, inside of this function, and ask them to make the predictions using the probability predict function, right? So you'll get the outputs, and you should do that on the validation data, okay? So basically, this function is going to be used in the next step to create a stack. But what we need to do is for all of the trained base estimators, so we're using the estimators in a voting ensemble to be the base estimators for a stack that you'll build, right? So all those trained base estimators, you have to ask them, give me your predictions for the validation training set. Right? So you'll need some sort of a loop to do that. Access the estimators in this classifier, and then you'll actually ask them to give you the predictions on whatever data is given here. So when we test it, we just give you the training data, but that's not what we'll do when we create a stack here later on. So again, this is kind of subtle, but you shouldn't end up getting this wrong, because you should use these cells as are given in the assignment notebook here. So anyway, whatever data you're given, you have to get the output, the predictions for that input data, and you have to stack them all together, and that's what's expected to be returned from here. So since, like if the training data, so the easiest way to understand this is one thing that's tested is you just end up with the right shape. So if the training data has 5,000 samples, when you ask for the predicted outputs, since this is a binary classification task, there's going to be 2 outputs for every one of the 5,000 input samples, right? The probability that it's class 0 and the probability that it's class 1, right? So if I have 5 estimators and I'm creating a stack on 5,000 samples, I should end up with a array that's returned that's shaped 5,000 by 10, right? Because I'm going to stack together all of the 2 outputs for the 5 base estimators that we have in the voting classifier, so I end up with 10 columns, so 10 outputs stacked together for each of however many samples that we pass in that you're supposed to create this stack from. All right. Once you have this, then it makes it a lot easier to create the stack. If you have this function, you can reuse it, and you do need to reuse it for the task 6 here. So, it is possible to make mistakes, so I'll emphasize it for you guys that are here, or people watching offline on the video. So the very final thing is you're supposed to create a stack and ensemble. So you need to reuse, you first need to reuse your function that creates a voting ensemble, right? Because we're not going to do a simple vote here, but we're just going to reuse that to train all the individual estimators. So instead of redoing your work to create the 5 estimators, just reuse your task 3 function. That will train and fit the 5 estimators. You need to do that on the training data. So that's the first pair of data that's passed in to the task 6 data. Then once you do that, you'll have a voting classifier, but we're not going to use soft or hard voting. Instead, you're supposed to train an additional classifier that will be trained on the outputs from the base estimators to figure out the overall prediction that you want to make. All right. So in this one, you need to reuse the task 3 function first. So train some base estimators on the training data. Once you have the base estimators and the voting classifier, you want to reuse your create stack data from the previous task to create a stack of data on the validation data. Right. So here's where, so I'm giving hints to the people listening to this that you have to be careful, make sure you're using the right data here. So this will generate a new set of stacked data on the second data set. And you're going to train an individual support vector classifier on that stacked data set to make predictions. Right? So when you train your support vector classifier, you'll need the stacked data, and you'll need these labels, the Y validation labels, to train it up. Okay, and I skipped over, but I did ask you on task 4 to also, just for practice, to show the confusion matrix and plot the AOC curve. So if you were doing this for a competition, probably the receiver operator characteristic area under the curve plots would be really important for this task here. So I probably should have had you do it for the first task 3 as well, because we might want to compare that performance for the voting ensembles, for the bagging ensemble, and then for the stacking ensemble. But I did ask you to plot that here, and then also to do that on task 6. So if you do the task 6 correctly, we ask you to return 2 things. So return the voting ensemble, but that's just the thing that's created from reusing your task 3 function, but also return this blending estimator, which should be a support vector classifier that's trained on the stacked data from the base estimators in the voting ensemble. All right. So once you have those, I ask you to report the accuracy on the training and the validation data. So this isn't as straightforward as any of the ones before. So to do this, hopefully I described this here. Yeah, so to do this, you have to recreate a little bit of the work you just did in the function. But basically, you can reuse your function to create stack, because the estimator that's returned here was, so this first one is what you're going to be testing here. But it's expecting, this blending estimator is expecting a stacked data set, the result of taking the data through the base estimators, right? So to do this, I mean, you can't just pass in like if I ask for the training, the accuracy on the training data set, you can't just pass in the raw training data set, because that's not the right shape that's expecting. You have to take this training data set, pass it through all the base estimators, stack their output. The output from those on the training data is what the blending estimator would be expecting in this case. Same thing for this. So if you can do it again, but you can stack the validation data, that will give you a stacked data set. That is what would be the expected input for your blender. So you have to do a little bit extra here to report on the training and validation. But I did this kind of for a point here. If you follow this assignment, you maybe didn't quite understand from reading about what a stack is, a stacking ensemble was. But here you should be able to understand and see, the things that are returned, the base estimators here in the voting ensemble, they were trained using the training data, right? But the blender, we didn't want to retrain it on the training data. That would be leaking things. So we train it on you need to train it on a different data set. We used the second data set, the validation data set, for that, right? But the result is that the stack that we want to do, we've used both the training data and the validation data set to create that stack. So it's really not fair. You're going to get inflated performance if we ask it to make predictions again, the stack to make predictions again on the training data or the validation data. So one layer or the other has already seen that data and was already trained on that. Right? So to get a fair prediction, we need a completely new data set. And at this point in the assignment, you've never used that third one, the test data set. So this is the only place you need to use it. But to get a fair report on the accuracy, I asked you to determine the accuracy on that third test data set and do the confusion matrix and the ROC curves again. You could compare this back to the bagging one, although it's probably more fair to compare this to the soft and the hard voting ensemble, because basically the stack that we do on task 6 is using the same base estimators as we use on task 3, but instead of doing a simple vote, we do something more complicated. We build a new classifier to determine what prediction that we're going to do. Right? And you should find that usually it will at least match the performance of the soft voting classifier. So the soft voting classifier should usually have a bit of a performance gain over the hard voting classifier, and it looks like it's probably a significant difference. In this case, you may or may not get a little bit of a gain over the best of the soft or the hard classifier, but usually you do. It may not be significant, but it'll tend to be a bit better there. So. All right, and yeah, if we wanted, it's a bit unfair because we allow you to try and tune the bag of trees, but yeah, if we wanted to compare the stacking ensemble to like the bag of trees, we would probably want to go in and try and tune the individual base estimators to improve their performance a bit, and then we would have something that would be more directly comparable to the bag of trees that we create on this assignment. But we didn't ask you to do that on this one here. So. All right, so let me know if people have questions on that. One other note on this, you might find, especially when you have to train the voting ensembles, that it does take some time. In my testing, it never, so when you make your commit and push it to GitHub, it never exceeds the time limit. But there's like a time limit of 10 minutes for each one of the tasks. So, but it might take 5 or 6 minutes, or it usually took me about 5 minutes for the most, for the task that took the most amount of work to have it run that and run the tests. Depending on your, the power of the system you have, you might get more time. It might take you longer. Hopefully not prohibitively so. Let me know if anybody's having performance issues. But like I said, this isn't a good workflow, but it does. It is able to complete using the GitHub workflow. So even though the longest task is when you run it on GitHub, so when you send a push to GitHub, the very first task reruns your whole notebook. So it kind of as a reminder, your notebooks do have to run cleanly, every cell from top to bottom, before I'll grade them. But rerunning the notebook means that basically every one of your task functions is run and the tests are run. So that is running everything that's individually run after that. So for me, when I ran it on GitHub, it usually took a bit over 5 or 6 minutes, but it did complete. It doesn't time out. It shouldn't. So unless you're doing something that's causing significantly more training when you create your base classifiers or something else. Okay, but yeah, just a heads up on that. I hope nobody has any performance problems, but let me know if you're having some issues, and we can see if there's anything we can do about it. Okay, yeah, so that's it for assignment 5. Let me know if anybody has any questions or needs any things clarified on the assignment. Okay, so let's move on to new stuff for a bit. So I get started on looking at principal component analysis and dimensionality reduction today. So I already mentioned, but kind of as a reminder, I hadn't realized I didn't have all the notebooks up in our class repository, so you might have to do a poll if you want to see the lecture notebooks on PCA and unsupervised learning, that kind of stuff. So they might not be in there if you haven't done a poll today. So give me a second. Let me reopen up our lecture notebooks here. All right. So, look at here. If you do a poll, you should see now that in the main lecture notebooks, there's 2 more. So I'm going to follow our hands-on machine learning textbook. It first talks about PCA in chapter 8. I want to open up my textbook here real quickly too. So, yeah, for our last 2.5 weeks, this is actually a new topic. Okay, so I hope everybody's aware of that. So you should be aware that up to this point in the class, we have exclusively focused on supervised learning, all right? And I hope everybody's clear at this point with what we mean by that, right? So we've looked at 2 types of supervised learning, regression and classification. But that means that when we build a model, an estimator, a classifier, we build it, we figure out the parameters for the model, or however the model is created. We build that by giving it a set of inputs and giving it the correct answers, the labels for those inputs, right? So that's the heart of supervised learning. So we give it some data and the correct answers. It uses that to build a model, and then we can ask it to make predictions on data it hasn't seen, right? The better we are at building a model using supervised learning, the better it can generalize and make correct predictions on stuff that it has never seen before. Right? So in unsupervised learning, so dimensionality reduction, principal component analysis, and clustering will be the 3 main things I'm going to look at over the next 3 weeks here. The goal when we're doing unsupervised learning is to do some sort of a transformation on the data, and the data itself will figure out what the correct groupings are, or what the most important features are, or things like that, okay? So for all these mechanisms we're going to look at chapter 8 and 9, we don't give it the correct answers. So we can ask it to, in the first chapter when we look at dimensionality reduction, we can ask it to do that on a set of data that we don't know the labels, the answers for. As we'll get into today maybe, we can use that for doing things like compression, for figuring out the importance of features on our new transformed data set, and some other things. Okay, so we can do these both here and clustering that we'll talk about after we get back from Thanksgiving, without it knowing ahead of time, what people consider are the right answers for, in terms of what the most important features are, or which features are most related to which other features. Okay. So if you've read the chapter 8 from our hands-on machine learning, it starts off with a little bit of discussion. It's a little bit abstract, but let me try and just real quickly give you an idea. So big data is hard there's many different reasons. Just once you have lots of data, it might be too big for it to fit in your memory, and other things like that. But intrinsically, mathematically, big data, when I have a large number of features, that means that the thing I'm trying to represent is high dimensional. And very often, answers or things behave much differently in a low dimensional setting versus in a high dimensional setting. So I think most people, if you think about it, can understand this argument that's made right here. Okay, so often when you have data that's really that's extreme on a feature, it will be problematic when you're building a model using that data, right? So like think about just one feature that ranges from 0 to 1. Okay, so that's what we're talking about, like with a unit square or a unit cube here, that we transform our data, we scale it so that every one of our features. So I don't know if it's clear. There's a relationship between, when we have a data set, we have some number of samples. 0, 1, up to n minus 1 for n samples. We have some number of features. This is the way I usually think of a data set, right? It's like two-dimensional. The inputs, features, and then we also have our labels, usually just like a single label. So, we have feature 0, feature 1, up to feature m minus 1 for m features in the data set. So if I want to represent or I want to model this data, every feature is going to be one dimension in the space of the model that I'm trying to fit to it. Again, thinking about supervised learning here. Right? So if I only have two features, I would just have two dimensions. Call it feature 0 and feature 1. And if we rescale them to be on the unit square, that would mean that all the feature values would range somewhere between 0 and 1. That's our unit square. So here, I guess you might have to just take my word for it, but values that are extreme tend to be more problematic in fitting a model than values that aren't. So in this case, values that are extreme are going to be things that are either close to 0 on feature 0 or close to 1, or close to 0 or 1 on feature 1. Right? So the example from the textbook is imagine that you're generating the value of these features at random, and what's the chance that something is 0.001 from the border? Right? So being that close to the border is percentage-wise, if I generate 100 numbers, I would expect, if I generate 100 numbers, I would expect 0.1 percentage of the numbers, so not 1%, but 0.1% of the numbers to be within either between 0 and 0.001 or 0.999 and 1.0, right, to be extreme. So I have 0.1% of being here or 0.1% of being there. So I have a 20% of being kind of that extreme along my feature 0 dimension. And the same 20%. So sorry, not 20%, but 0.2%. And the same argument can be made for the other dimension. Right? So in a two-dimensional space, there's just a 0.4% of a chance, if I'm just generating values at random, that it will be somewhere within that bounds, somewhere within close to 0.001 of the edge here. Right? And again, I don't know if that's a good argument for it, but those can be problematic when we're building a model. Right? Extreme values like that will be more problematic than values that are kind of all clustered together, closer together in the space that we need to model. So that's not a very big chance, but the non-intuitive part here, and this is a good thing to try and understand, at least at this high level, intuitively here. So the curse of dimensionality, that even though I have a very small chance, if the data really is random, when I'm low dimensional, like 2 dimensions, I pretty much am guaranteed that if I have a 10,000 dimensional, so if M is 10,000, and if I generate each feature at random among the 10,000, I'm very likely, so there's a 0.2% chance that each feature generated at random will be close to a border, but I've got 10,000 of those I'm randomly sampling, right? So it's basically a 0.2 times 10,000. So anyway, even though most of the features if I'm generated at random will be somewhere far away from a border, once you get to high dimensional, you're guaranteed that one or a couple of those features are going to be extreme, right? So you're guaranteed that. The takeaway of that is low dimensional data. I'm much less likely to have extreme values in my samples, so I won't have these issues that can cause problems with different kinds of ways of modeling that data mathematically. But when it's high dimensional, I'm very likely every one of my sample values is going to have one or a couple of the features that's close to, that's an extreme in terms of that range, right? Be an outlier at least on one of my 10,000 or 100,000 features, whatever my high dimensional big data set is. And so, one intuitive reason why that is that if things are extreme, they non-intuitively, everything is relatively close in terms of distance in a low-dimensional space. But things become very sparse in a high-dimensional space. So you're guaranteed that one or a couple of my dimensions are going to be extreme, which means everything is going to be really far away from each other. Just looking at the distance. So it's much tougher to figure out the similarity if I have a very big data set, a very high dimensional data set. So in theory, we can either increase the data set size, so even though we're guaranteed to have some extreme stuff, if you have a lot more samples, we're much more likely to more densely cover my really high dimensional space. And that'll make things work better in terms of modeling stuff. But that's not always possible, although that's one of the reasons why big data works. So for a high dimensional, if I have large number of features, but if I have a small number of samples, I might not be able to model it very well, but magically, if I have a large number of samples, I will increase the density, and my models might start working. Right? So big data can even though you got to have the processing power to handle the big data, I can start to get good models. That's really kind of what's happening with large language models. They're really training on, it's a very huge dimensional space, but they're using large amounts of training data to get to get coverage of the space pretty well. So another common solution, though, is if we could do something to reduce the number of dimensions, a lot of these problems go away, right? So this curse of dimensionality goes away if I can somehow, instead of using 10,000, reduce that down to the 100 most important dimensions, right? Okay, so that's really kind of what we're talking about in this chapter. Is this week is dimensionality reduction. It's one of the main things, right? So there's a couple of different unsupervised learning methods you can use to do dimensionality reduction. Okay. The two kind of main classes of these, I don't really have this in the notebook, but you can talk about projection or something more complex called manifold learning. And principal component analysis is really a projection kind of method for dimensionality reduction. So Projection, I mean, hopefully everybody can understand the basics of this. It's relatively simple. You know, these are mathematical techniques, but you know, if I have three-dimensional data, I can reduce it to two dimensions using projection. So if I just select a two-dimensional plane, like it's trying to be shown here, it might be a little bit tough to see exactly what they're trying to say here. But supposedly this is the two-dimensional plane that was selected, that's defined by these two vectors that are trying to be shown here. So the data that's originally in three dimensions, we just project it to the nearest point in the two-dimensional space. Right? So that reduces it from 3 to 2 dimensions. Right? And that's really all, you know, to jump to the chase, that's really all that principal component analysis is doing. In principal component analysis, we take a really high dimensional space, but we figure out a good set of lower dimensions that contain most of the information in that data set. And PCA can do it without you telling, you know, without you giving it information. So it's an unsupervised technique. So it figures out the good plane in this case for three-dimensional, and then you can use that, you know, whatever are the most important dimensions that you have in that space, you can use that to get rid of the lesser ones and project down into your lower dimensional space. All right, that's kind of high-level, hand-wavy description of what PCA is doing. Okay. So yeah, if you didn't do the reading, that PCA, dimensionality reduction, doesn't always work well for all kinds of things. So sometimes you can have data that's high dimensional, but it's really kind of wrapped around, right? So projecting all this from 3 dimensions into 2 dimensions, the colors here, if you didn't read this, are supposed to represent probably like classes. So this is probably like a multi-class classification. So, you know, the black is one class, and the red is one, and the light yellow, so we got like 5 or 6 different classes here. So if we, no matter what plane we would select for projection, we're going to kind of lose a lot of the information of this, what's known as a manifold mathematically, this kind of curvy thing, this two-dimensional curvy thing that happens in the three-dimensional space here. And it's a little bit beyond the scope of this class. I mean, there's whole branches of mathematics about you know, representing manifolds like this and finding them and calculating them, stuff like that. So yeah, I don't know if this is a good illustration. So just imagine that we just project all this. We remove the x3 dimension and project everything down to x1 and 2. Right, so I think that's kind of what they do here, if I remember on the textbook here. So you know, we lose a lot of the structure in the three-dimensional data. Everything gets mixed together. If we could somehow, instead of having a plane, create a manifold that kind of follows the roll here and project onto that manifold. The manifold is two-dimensional, but it's not a plane. It's a curvy kind of thing. So think of like a roll, like a roll from a toilet paper or something like that. If we could project onto that, we could preserve the structure. All right. So that's probably all I'll say about the manifold learning. There are I haven't done a lot with it. There are some, if I remember right, there are some things in scikit-learn that you can try to do projecting onto some manifolds. So I guess our textbook doesn't really show any example of that, though. Okay, so let's go. The rest of the time I'll spend looking at principal component analysis, PCA. All right, so PCA can be used for dimensionality reduction and by projection, okay, the first method that we talked about, as well as some other stuff. So once you can do that, we can use this for for reducing our number of dimensions on our data set, and other things. So here, I guess I do have the stuff, the notebook that I just put up today, recreates a lot of this stuff here. So this isn't exactly the same data set from the textbook. Let's say that this is our data, just two-dimensional in this case. And we want to use projection to reduce it to one dimension. All right? So this picture is the best one from the textbook. I don't have exact duplication of it. So the idea for the way that principal component analysis works is, we don't want to just project it on, like in this case, like it's shown here, we could have just projected onto the x-axis, right? So that's kind of similar to the C3 here, right? So this is C2, this is C3, and this is C1, right? So the idea, think of just the regular x-axis. If we projected everything onto the x-axis, we would just be, this point would go here, and this point would go here. Everything would go to the corresponding place on there. Or we're doing the same thing like for C3, but if that's our axis, then this point, we're going to project. We're always projecting orthogonally to the dimension that we have. So here in right angles to the dimension. So we'd have to get a right angle from here to there for our projection for like this one. So the idea is, this is the important part here, is depending on which of the lines or the planes that we select for the projection, we're going to preserve more or less of the variance. All right. So in two dimensions, we can only reduce it down to one dimension. So this is the simplest possible case of projection here. There's going to be exactly one line or one plane or one hyperplane that will preserve the most variance when we do projection. And that's what the mathematical technique of actually support vector machines. So PCA actually uses SVM, support vector, sorry, not support vector, I'm confused. Single value decomposition, so SVD. Confusing support vector machine. So principal component analysis is really just a wrapper around a well-known technique that's been around a long time, but once machine learning became a thing, it got rolled into doing this, and we do this kind of dimensionality reduction. So in support vector decomposition, it's doing exactly this, and you don't have to exactly know how it does it or the details of the mathematics, as long as you understand at this level, right? So what we're discussing here, if I want to do dimensionality reduction to one dimension, I want to find the dimension that will preserve the variance. What that means is I need the dimension where I will have the data spread out the furthest, right? So that's known as the principal component or the principal dimension. And SVD, support value decomposition, does that automatically. Right, so you can put it in. It's a matrix algebra technique. So you can put in your original set of data, and it will figure out what the vector or the plane is for the most important component, the one that if you project it onto, will give you preserve the most variance, the most information. All right, and it works for multiple dimensions. Okay, so in this case, when I have two-dimensional data, all the dimensions that are found by SVD are orthogonal to one another. So once I figure out the principal dimension, the principal component, the second dimension is fixed. It has to be the one that's 90 degrees from the principal component. All right, but if my dimension it was three-dimensional and I was going to do principal component analysis, once I figure out the first dimension, I would have two two more dimensions, two more orthogonal directions, right? So SVD in the three-dimensional data would figure out the first principal component and then the second one, the second dimension that ignoring the first dimension, the one that gives the second most amount of variance that's preserved when we project onto it. Okay, does that make sense? So this is an important thing to understand, right? Just at a high level conceptually. I mean, SVD, it's not all that tough if you want to look at the details of the linear algebra to implement SVD. In fact, we'll probably have to do a little bit of that by hand on the 6th assignment here. But there's some examples of calling SVD directly to do this, to figure out the principal components here. So let me go back to my lecture notebook. So here, this will probably be about the last thing I'll do today. We've got plenty of stuff we can talk about on Thursday then. So here we're just using data pretty similar to what was shown in the textbooks. Not exactly the same data, but similar. So it's two-dimensional, but it's been rotated. So the principal dimension is probably along this plane, and then of course since it's two-dimensional, the second principal dimension is going to be the one orthogonal, right angle to whatever we find is the principal dimension. So if you do a basic PCA, so the default, if you don't specify the number of components, is it will do SVD and preserve all of the dimensions, right? But you can do dimension reduction directly by asking for PCA and specifying the number of components. So if I have my data is two-dimensional here in X, if I specified PCA, if I just said keep one component, it would do the projection immediately down to the principal component here. But notice here when we use the fit transform, so the unsupervised learning methods, I mean, they still have the similar API. So there's a separate fit method and then a transform method. So here, and there's a fit transform that we do them both at the same time, right? So if we fit this principal component analysis to our original data X, what it does is it runs a singular value decomposition to figure out the direction of the first principal component and the direction of the second principal component, and the amount of variance that each one explains. Okay. So in the lecture notebook, if we look at just using PCA, so we do a fit and a transform on our original 2D-dimensional data. So since we're still using the same number of components, it doesn't do any dimensionality reduction. But notice after doing the fit transform, if we replot, so we call it X2D here, the new one. So if we replot it, it will look like that the data that now what was this vector here has now been rotated, shifted, so it's directly on the x-axis, right? So this is the principal component that keeps the most amount of variance in our data. Was projected onto something like the C1 vector. That's what the SVD found was C1 was the principal component vector here. And then, of course, for two-dimensional data, the other one is set, but the other dimension is orthogonal to that. So yeah, notice if we want to do projection, all we have to do is just use whichever dimensions that we want to use, right? Throw away the rest. So now, after doing PCA, the most important dimension is at column 0, index 0 of our transform data. And the second most important one is in column 1. And, again, if I had very high dimensional data, so if I did this on a data set that was 10,000 dimensional, afterwards, the most important one, the one that keeps the most amount of information, will now be projected onto column 0, dimension 0. The second most important one, dimension 1, and so on. So to do dimensionality reduction, all I have to do is just keep the dimension, whichever dimensions that I want, up to some number that I think is a good number of them. Right? So over here, if I just want to keep the first dimension, this is a projection of the original data onto the most important dimension. Right? And here we're projecting the data onto the second dimension. Right? So here is the projection onto what was labeled as C2 kind of in our textbook, right? So here we're projecting all these data points onto this vector here. Okay, so yeah, that's a good stopping point. So at this point, I've got some stuff where we're going to try to go into a little bit more detail of how that works, but I'm going to leave that for Thursday before we get into it. So yep, so let's stop there for today. I'll let you guys go then. Yep, that's it. So yeah, I only saw about 5 or 6 people have accepted the assignment 5 so far. So if you haven't accepted assignment 5, I'd really suggest you get started on it. I think this will take people more time than the previous assignment 4. So take that into account. Keep working on your final project as well. All right, I'll let you guys go.